So we have started looking at these functions which calculate the slope of a curve at any point along that curve. Okay, so we call this function a derivative. So this function gives us the instantaneous or tangent line slope for that graph. Okay, so we work this out when we can work out each individual slope coordinate. Okay, we know that we can find out slopes using a limit. And since we can come up with a series of slope points, we can establish that it's a function, and we've allowed ourselves to calculate this function by using essentially the same process of calculating slope at a point, but just generalizing that point for x. Okay, so this is a derivative, and this process is called differentiation. Now, in order to get instantaneous slope, or in other words, the derivative, we must have some constraints on this function because there are some points of graphs that we cannot find instantaneous slopes. For example, and we kind of alluded to this before, there's this bend or kink in the graph here. Okay, at that point, there's no distinguishable slope. In fact, if we use a limit, the slope limit coming from this side, well, the slope looks like that. Okay, slope coming from the other side, the slope looks like that. And the two slopes do not meet at any point. So these bends in the graphs or kinks in the graphs are not permissible. So in order to be able to find a derivative, or in other words, differentiate something, we need this graph to be smooth. Okay, so this has to be smooth. So not only does it have to be smooth, so this graph here is smooth, but it also has to be continuous, because if it breaks apart like these ones do, the endpoints are not differentiable. So the derivatives are not defined at these endpoints because, again, from one side we're getting one slope, from the other side we're getting a different slope, and a graph also breaks apart. So the condition for being able to find a slope function is that the function has to be smooth and continuous. Otherwise, when we apply a limit, there are places where the limit may not work. So this is not differentiable at that point here. So I'm just going to highlight them here. So along there it's not differentiable, along there it's not differentiable, along there it's not differentiable. Those are non-differentiable points because we cannot have a limit that gives us the same slope from both sides. Okay, so this is a problem. So this is one of the constraints of differentiability. It must be smooth and continuous. And the reverse is then true. If we can say something is differentiable or has a derivative, this implies that the graph of the function is smooth and continuous. So we're basically trying to find slope, okay, or rates of change. This is what calculus is all about rates of change and how things change. And we're going to start using this notation. And this notation, we kind of used this notation the other day. This little prime, it's called that little thing mark, it's called a prime. This is called f prime of x, or in other words, the derivative of f, or the slope function of f, the function that calculates instantaneous slope on this graph. This y prime is the same thing. It's the y prime is the derivative function of y, or the function that calculates the slope values of the function y. So this is what was developed by Newton. There's another guy who kind of developed calculus about the same time. His name was Leibniz, and he used this other notation here. This notation actually makes a little bit more sense because this essentially says d f of x, so change in f of x over change in dx, okay, or change in x. Well, that slope, change in y over change in x, is the derivative of f, okay, the slope function of f of x. Or here we can more clearly, the change in y over change in x, yeah, that's a slope function that calculates slopes on the original graph y. Okay, so this is the notation we're going to start using. We will use this interchangeably, so make sure that you're clear on this new notation.